Hello students, so welcome to part 6 of the lecture series on previous year gate questions of electronics and communication on the topic of network theorems. We have already completed 5 parts. Now this is the 6th part and this is brought to you by EDAMIGO team. Now let's move directly to the questions. So this is a very simple question. Here we have to find the value of RL for maximum power transfer. Okay, now for maximum power transfer, we know that for maximum power transfer RL is equals to RTH. Now to find RTH, let's first of all copy the figure. Okay, so to find out RTH, we will first of all remove this this resistance RL from the figure. So we will remove the RL from the figure and then we will calculate RAB or RTH. Then the value of RL should be equal to RTH for maximum power transfer. Now we also know that to find out RTH, now since all these sources are independent sources, so these independent sources are removed for calculating RTH. So the current source is open circuited, voltage source is short circuited, and this voltage source is also short circuited. So we will short circuit these two sources. First of all, we will remove it. We will also remove the current source. We will also remove the voltage source. Now we will short circuit the voltage sources and we will keep the current source as open circuit. Now very simple question, we can easily see that these two resistances are in parallel and the combination is in series with 10 ohms. So RTH is equals to 10 plus 10 parallel 10, that is 15 ohms. So the answer to this is C. A very simple question. Right, so now let's move on to the next question. So here we have to find the value of RL for maximum power transfer to RL. So this is your RL. So again here we have to find the Thevenin equivalent resistance seen across the terminals of the load RL. Now let me just reduce the size. Now so here let us mark point node A and node B and we will remove the load RL and we will find the RTH or RAB. So RL has to be equals to RTH for maximum power transfer. Now to calculate RAB, we will short circuit this independent voltage source. So the circuit will be like this. The dependent voltage source, okay, so we have short circuited it. Now since the circuit has a dependent voltage source, so to find out RAB, we actually apply a voltage source V0 which has a current I0 coming out from it. So RTH will be V0 upon I0. Okay, now Now, as we know that, so let us assume that this node is grounded. So this is grounded node. So this is at 0 voltage. Okay. So let us assume that this node is B, this node is A. So from the given conditions we can say that node A is also at voltage Vx, node B is also at potential Vx. Okay. Now let us assume that this node is C. Now since this is grounded, this node D is grounded, so C node will be at potential V0 because of this battery. So we can see that both the resistance 4 ohm resistances will have equal potential across themselves. So equal current will flow through these two resistances. Equal current will flow through these two resistances. Now the incoming current is I0 and these two current has to be same, so these two current has to be equal to I0 by 2. Okay. Now if we apply a KVL in this loop, that is from C to A to D, and then from D to C. Now from C to A, the drop will be plus minus. We are entering at plus, so it is I by 2 into 4. Now from A to D again, it is plus minus, so it is plus I by 2 into 4 A to D. Then from D to C, since we are entering from the negative polarity or negative terminal of V0, so it is minus V0 is equals to 0. So from here we can see that V0 is equal to 4 I0. Okay, so these are the I0 currents. Okay, 4 I0s, or we can say that R equivalent is equals to 4 ohms. So this is the answer to this question. Okay, so now let's solve another question. So here we have to find the Thevenin equivalent impedance ZTH seen between the nodes B, P and Q. So between these two nodes. So first of all, let me copy the figure. A very simple question, there is no more trick in the question. Okay, now here we can see that since there are two sources, this is one source and this is another source, and both the sources are independent sources. So to find RPQ, we will first of all remove these two independent sources. So the voltage source is actually short circuited and the current source is open circuited. Okay, now since there is no dependent source, we can easily find the resistance or impedance, we can say ZPQ. So P and Q, capacitance is 1 upon S, resistance is 1, then inductance is S and resistance is 1. So we can say that this ZPQ, so these two are in series combination, these two are in series combination, and both these two are in parallel combination. So it is 1 upon 1, sorry, 1 plus 1 upon S parallel 1 plus S. So equivalent impedance will be 1 plus 1 upon S into 1 plus S divided by 1 plus S, 1 plus 1 upon S plus 1 plus S. So the answer to this is s plus 1 whole square divided by s plus 1 plus s square. So it is s plus 1 whole square divided by s square plus 2s plus 1. So that is equal to 1. Okay. So equivalent impedance of the circuit is equal to 1. So we have solved the questions of previous year. So I'm ending this part here itself. So thank you guys. Stay tuned and we will be solving in the next part more questions from the network theorem topic. Thank you.